But if we do turn this on, could you monitor that with the headphones and see if my voice is coming through with that mic? Testing, testing. Good? Okay, we'll try that. Okay, so we have some viewers on our live stream as well, which actually is a great transition to this section here. This is the Kopernik Observatory YouTube channel, and we do, if I refresh this page, you'll see that we are now streaming this Winter Skies program live. And so we have some viewers on there that we want to make sure they are getting the audio on our end too. If you ever want to tune into one of our Friday night programs, they will show up here. Winter Star Party is already scheduled, as you can see. Our full spring slate will show up here as well. And also observing live streams. So in the live section, you'll find our last observing live stream was on the annular solar eclipse on October 14th of 2023. And so you can actually go back and watch our show there. Now, before I get into my main program for the evening, I do want to jump us over to this news here that you may have seen pop up in over the last week. So since 2021, when the Mars Perseverance rover landed on the red planet, it brought along with it a friend called Ingenuity. It's the first powered aircraft beyond Earth. So it uses, it's basically like a little mini helicopter, a mini drone that flies around in the very thin atmosphere of Mars. And it was really, it started out just as an experiment and turned into something much more. It actually became a scouting mission for Perseverance. So Ingenuity could fly ahead of Percy and map out its path, see what was ahead of it, and then Percy could drive there, knowing what obstacles were ahead. So it was a really cool partner mission, and they only expected it to last a month. Like I said, it was an experiment, so they were hoping they could get 5 flights out of it. And they got, I believe the number is 72. It was on its 72nd flight when it finally, it technically still able to communicate with it, but one of its blades got damaged. And now it can no longer fly, no longer a flight-worthy aircraft. But they actually, the way they determined that, because Percy can't skip, they use the shadow of the blades and the cameras on Ingenuity to see that the blade had been damaged. So as of right now, Percy can't see Ingenuity. It's unclear whether it ever will be able to, based on where Ingenuity is at the moment, but maybe one day we'll get another look at that aircraft. But that was the kind of sad news. It lasted way longer than it was supposed to, like so many of these Mars missions do. But all the same, it's a little sad that we lost Ingenuity's ability to fly. But it's not the end-all be-all of powered aircraft on other planets. They will be sending other ones like the Dragonfly, which will be sent to Titan, which is one of Saturn's moons. And that is the outright drone, and it is the mission. It's not tied in with any extra rover. It's the mission they're sending there is this drone, this powered aircraft. So that'll be exciting too. So a very successful experiment. Okay, so that was just some current events, and I always like to share that when something exciting happened. Okay, so let's jump into this, our Winter Skies program. So Winter Skies is both designed to be a great introduction if you're just learning how to read the night sky and learning the basics of how we map these things out, and also what's out there in the sky for this season. So there's 2 main parts to it. And also, just while I'm thinking about it, don't let me forget that I do have maps for you all today that you can take home for this season's sky. Okay, so let's get into our program. Actually, we're going to skip this slide because I can just talk about that. some of the things we'll discuss are these ABCs of stargazing. That'll be the first section, just like that introduction. And then we'll get into what's out there in the sky, like maybe some satellites that you can see. How do we determine a satellite from an aircraft or a star or a planet? And then we'll get into any planets that are out, stars that are out, and deep sky objects. And if you don't know what those are, we'll discuss those too. So starting with the ABCs of stargazing. A is for angular size and distance. So this is one really easy way that we can work together to figure out where things are in the sky. It gives us a language to go on. So let's look at this. The best tool you have for communicating where the distance between objects, the distance from the horizon and so on, is right here. So these are depicting different angular distances you can use with one finger, multiple fingers, your fist, and this is at arm's length. So when you hold your arm at arm's length and you put your index finger up, the width of your index finger pointing out in the sky is 1 degree. So that's an angular distance. So 1 degree, then you have your 3 fingers up, and that's 5 degrees. A fist would be 10 degrees. Your pinky and index finger spaced out, that is 15 degrees. And with those, you can start measuring the distance between stars. So we have a picture of the Big Dipper there. And this is not necessarily something that's going to work as a demo inside here because we're all at different distances relative to the screen. What's great about the sky is everything's so far away, it doesn't matter where you are. We're all able to see the same stars and at the same distances. So there's no change in perspective really on that. So in this case though, you can measure across the length of the Big Dipper 25 degrees with your hand. And this becomes handy when you're trying to communicate where an object is. If you're trying to talk about like how far is this planet from this bright constellation, you can do the same hand gestures. You point out one bright star, you try and point out the planet, and you can measure those distances between them. So that is a important start also to the C that we'll get to in just a moment, because they also use degrees as a measurement. So there's our A for angular distance. B is for brightness. So when we look out at the sky, we also see that the objects are at different magnitudes. They're at different brightnesses. Stars are at different brightnesses from one another. Planets will, at least the main visible planets, will be very bright in the sky. So when we talk about magnitude, we're trying to compare those luminosities, those brightness levels. And this is a diagram that, just a number line basically, that maps out across this number scale where objects fall. So immediately the first thing you'll see here is that we have negative numbers on this side, like you'd expect for a number line. But way over at the furthest end of it, the lowest number is the sun. That's a little weird. Okay, and then on the other side, in our positive numbers, we have things like the Ring Nebula. This point here even points out that at around 6 on our number scale, that's the faintest naked eye object, meaning the faintest object that you can see with just your eye. And the reason for that is because of the way early astronomy worked and how early astronomers mapped out and categorized the objects that they could see. So your first magnitude stars would have been considered the brightest. So they're kind of ranking them. This was many, many years ago, hundreds and hundreds of years ago. even with just the Greek philosophers. And so they would rate, okay, the first magnitude star is the brightest, it gets first place. Second magnitude would be a little dimmer, third magnitude dimmer, and so on. And over time, as astronomers continue to use this idea, because astronomy itself is among the oldest of the sciences, and as they continue to use that, they just kind of never dropped it, even once they could actually measure, we have the tools to measure true luminosity of stars. So instead, they just translated what they were already using real data. And that's why we have positive numbers on this side, negative numbers on the other side, for brighter objects and dimmer objects. So going through some of these, you're heading towards -30 for the sun, and then you have the full moon heading towards around -12 or 13. Jupiter, one of the brightest of the objects that are out there, and often the brightest planet that's out in the sky would be like a 3, a -3. Then we get to this 0 point, which in our sky is a really good 0 point is Vega, a fairly bright star, part of the summer triangle. Going up the scale towards 3 and 4, we have the Andromeda Galaxy. We talked about the faintest objects you can see. Then heading into the Ring Nebula. And then out here is a lot of stuff that even our telescopes would struggle to pick up. And then way out here, you're talking about what is the James Webb Space Telescope doing? What is it finding out in the sky? So that's our brightness scale. And when you see brightness reported in a star map or on some of the applications we'll look at today, that's what we're talking about. Those are the numbers we'll see. And in general, really all that's worth remembering is that positives are going to be dimmer, negatives are going to be brighter. So that's our brightness scale. And then C is for coordinates. So we're going to go through 2 coordinate systems today. And actually, I'm going to grab this back here, this globe, because it's a great tool to learn about coordinates. I have my card here that I can put it on. So we're going to start with this altitude azimuth coordinates. And this is a useful system for when you're, again, like kind of you could potentially use just your hand as that tool to map out the degrees in the sky. And as long as you know where the numbers start, so north, south, east, west over here. So north is our 0 degrees. For our azimuth, azimuth goes around you, 360 degrees around. And then altitude climbs up in the sky to 90 degrees. So there's our 90-degree altitude there. And then for a given object in our sky, we can give it an altitude and azimuth coordinate. This is the simpler coordinate system. And because it's relative to the observer, meaning you're looking up at the sky at a star at an instant in time, and you can measure its altitude and azimuth. But in the next instant, that star will have appeared to move through the sky a little bit, and it will have a different altitude azimuth coordinate. And that's because the Earth spins. And because the Earth spins, that makes it appear that those objects in the sky are moving. So your altitude and azimuth is not specific to a given object. But it is the easier system to use. If you have, perhaps if you have a telescope, for instance, a lot of beginner telescopes will use altitude azimuth mounts. And we have a couple of those outside as well. I think there might even be one in the store there that's on altitude azimuth. Oh, that might be a tutorial now that I think about it. But anyways, regardless, they can be very useful scopes, and Dobsonians that we have outside too, those are also examples of altitude azimuth. If next time you come up on a clear night, you would certainly see those outside. And those just swivel on a base. We can even use the cart as a demonstration. They'll swivel like this, remember 360 degrees around you, and then they will move up and down in altitude. So both for scopes and for your personal viewing, altitude azimuth is really straightforward. But then it is helpful to map out the sky in terms of how what's called the celestial sphere behaves. Do you see Earth there in the center? So the celestial sphere is our view of the sky. It's a globular view of the sky, like you see here. I bring it up a little bit closer to everyone. You'll see both back here and on this, there are stars on our celestial sphere. And over the course of human lifetimes, even of course of 1,000 years, the stars are roughly in the same place relative to each other. The star map stays the same. Now, over much longer time spans, the stars will change. But for our sake, the celestial sphere is pretty consistent. And because of that, you can map out the celestial sphere. And in our case, we can make this equatorial coordinate system by projecting a lot of what we see from our perspective on Earth and how we map out our planet. So I'll use my mouse for this. If you look here, this red line going all the way around, that's called the celestial equator. And that lines up perfectly with Earth's equator. You just take Earth's equator and stretch it beyond Earth. And that it makes up the celestial equator. And you see along the celestial equator, starting with this vernal equinox point, says 0 hours. That is your right ascension measurement for these coordinates. So they go 1 hour, 2 hour, 3 hour, all the way around eastward along the globe, and then back to the star at 23 hour, or 24, I should say. So that's your right ascension. And then you also have declination, which may, in practice, it's kind of like your altitude. You can think of it out like that with your coordinates. It's going up along the globe. So here's your 0 degrees, and you climb up. And this is also a projection of Earth's latitude lines, right? Climbing up. And so, as a good example of this, the North Star, which in our case, this corner of the room is just about due north. You would find the North Star 42 degrees above our horizon, because that actually aligns with our latitude. So that gives you a little bit of a sense of how we can use charts like this and how we can use our coordinate systems. One more thing with the green line here that I haven't mentioned, this is the ecliptic. And the ecliptic represents the path of the sun throughout the entire year, how the sun appears to move. And that path has these specific points where we have the vernal equinox, and that's the spring equinox. So where the equator and the ecliptic cross paths. So we start our right ascension at that vernal equinox. So that's the equatorial system, and the best part about it is that you can find specific stars as specific coordinates on this. The coordinates don't move without the stars, they move together. So everything is really relative to our celestial sphere instead of being relative to Earth, or rather relative to the observer. Okay, equatorial. And there are telescopes too that will use equatorial mounts. And we allow actually every single one of our dome telescopes that are tracking mounts, they will use an equatorial system to navigate because the tracking is much better. It's keeping up with Earth's rotation rather than having to fight against it using alt-azimuth coordinates. Okay, so I think we can get a better look from the observer's view, because we've been kind of thinking beyond the observer using this program called Stellarium. And this is a really powerful tool. And before I even move into this, I want to show you the webpage where you can access Stellarium. Stellarium can be found at stellarium.org. And you can download it for Linux, Mac, or Windows. Or if you just have a Chromebook or just want to use it on the web, in a web browser, there's the web-based version, which looks like this. So there are so many ways to use it. There's applications as well. You can see there's Stellarium Mobile for both app stores. So those are there too. And it is free on top of it all. It's open source software. A lot of, I think even our planetarium system uses Stellarium code as its base. So it's a really powerful tool. And I'm going to show you what it looks like when you've installed it. The installed version has a much richer tool set than the web-based version, so that's worth keeping in mind when you decide what one you want to try out first. Maybe you just want to ease into it with basic tools and then jump to the installed version. That could work very well. I'm going to full screen this. And move this to the right. First thing you'll see is navigating is really intuitive. You just click and you drag. And it's like having your very own planetarium. So we're set up for the current date and time, but our model of the sky is so strong that we can time travel as well, either using fast forward and rewind down here, or the clock here. So you could skip ahead by even years. This is what 2025 looks like. You can see it, not much changes in the star field at least. You can change the months, change the days, or the hour, minutes, and seconds. And like I said, you can also just fast forward gradually through time. Go even faster. Go crazy. So, one helpful tip for using Stellarium, especially as you learn how to map out the sky, is to use your constellations. So you can just connect the stars, connect the dots, right, to draw out these pictures in the sky. And in the field of astronomy, majority of the constellations are based on Greek-Roman mythologies. So when you tour around, that's what you'll see. But what's also really cool about Stellarium, as long as I can find it, Starlore, yeah. So you can see where we have the Western constellations up, but you can go through and select any culture that you want and look at their constellations. So even though we use one set in astronomy to map out the sky, you can go through and look at these ones as well. Okay, and there are 88 constellations in total in our celestial sphere. And throughout the year, we only see approximately half of them at our location. And if you lived at the North Pole or the South Pole, you would only see a hemisphere's worth of constellations throughout the year. You would miss the entire other segment because the Earth is completely blocking them. For us, we get a little more variety because of where we are located at 42 degrees latitude. We'll have some things rising up at different seasons throughout the year. So we'll talk about some of these constellations throughout the program, especially as we get into deep sky objects and where we'll find them. Constellations are a great tool to use, especially the more conspicuous ones, because they can lead you towards dimmer objects like galaxies and nebulae and star clusters. So now I'll bring up the two equatorial systems one at a time so we don't go too crazy here. This is your altitude and azimuth grid, and these are right down here in the bottom toolbar. There's equatorial and there's azimuthal. So this is that first coordinate system we were talking about before. And when I start traveling through time, notice that the grid stays fixed in place to you as the observer, but the stars move through it over the course of the night as the Earth rotates. Now let's try the same thing again with the equatorial grid. You can see it gets really muddled when you have both of them on, so not recommended. But now let's start time traveling again the same rate and see what the equatorial grid does. How you see that the stars are almost locked along this grid, or the grid is locked along the stars. You could think about it either way. The only object over the course of a given night that's going to be noticeably moving through this grid is the moon. If we zoom in on the moon, and you see when you zoom in, you get a higher resolution grid. You can actually see it moving through the grid segments. And that's because it's the closest object to us. At least closest natural object. And because of that, and it has an orbit of about 27 days. So as it orbits Earth, you're actually able to notice the moon shift through the stars a little bit over the course of the night if you're observing long enough. But it's the only one that will be really noticeable out of the main objects. Planets are doing this as well because they're also in orbit, but they're much further away. So the motion isn't as apparent. So if you told someone that Jupiter has a set of equatorial coordinates for a given night, it's mostly the same from an observer's point of view. For telescopes, they will have to know that specific right ascension and declination at a given time, because it will change enough and you're zoomed in enough with a telescope that you can start to notice some shifting over the course of a day or a couple days. So there you do need to have some specificity. Okay, so that is a little bit on stellarium. We're going to continue to return to this platform. Oops, go over here. Let's go out of full screen mode. There we go. So let's jump back into our show. And now we can start moving into what's really out there in the sky this winter, now that we have some good background to work with. So I always like to start off with this one, the International Space Station, especially when our winter sky or our skies program aligns with a flyover, which this one does. And if the skies were clear, we would have gone out right at the start, because as you'll see, the timeline for it was right around 7:05, I think it was, for tonight's flyover. But this is one of the human-made objects that you can see in the sky. So here's an image of the International Space Station in orbit around Earth to give you a sense of size. The real scale of this object is about the size of a football field. And majority of that area is from the solar panels that you see there that power the craft. So This spacecraft is a low orbiting one. It is about 250 miles above our planet, which sounds like a lot, but that's the low Earth orbit occupied space. In fact, it is touching a bit of our atmosphere still, so enough where they actually have to boost it and get it going up at a higher orbit, because otherwise it would fall out of orbit over time. And it orbits once every 90 minutes at a speed of 17,500 miles per hour. Here's a nice figure to give you a sense of how fast that really is. I mean, it's already impressive that it's orbiting 250 miles up every 90 minutes, but give you a complete picture of this. You could travel from New York City to Los Angeles in around 9 minutes at that speed. So it is really booking it. And when we see the International Space Station fly over, it looks like a moving star. It'll be moving pretty quickly too. You can see on this chart here, tonight's flyover was actually relatively short. It goes from 7:05 p.m. to 7:07, and at which point actually gets up to its 19-degree highest point and then disappears because it enters Earth's shadow. But the 27th was so tomorrow night, if it's clear, starting in the northwest, you'll see it come up really bright, getting towards the same brightness as Jupiter, and that goes on for about 4 minutes to 6:21 p.m. And you see it flies northwest to northeast. The longest flyovers around the summertime when our skies don't get dark as early. You can see it fly from that western area heading towards the eastern area before it completely disappears. You get a almost full arc of the space station, and that's really impressive. And this is just one example of the satellite. Any satellite that will reflect light from the sun and reflect it well, you'll see it as this moving star through the sky. And we're starting to see more and more of these come out as a lot of stuff is getting launched into our into orbit. So like the biggest thing right now are the internet satellites that are being launched. Primarily right now it's by SpaceX. It's launching Starlink, but other companies are looking into it as well. And as that continues to scale up, we get more and more of these little stars moving through the sky that are just human-made satellites. So, and then there is another one on January 28th, another short one starting at 7:05 p.m. Higher altitude though. It'll climb up higher in the sky, so if you have a tree line at all, that one would be the better one to look for. Okay, so those are the timelines. Like I said, we would have, like tonight we would have gone out and observed this. There's a great website to go to look these up. You will also find the ISS in Stellarium. It will show up there too. But let's just briefly go over to this site here. This is called, and I did have it, but now it's gone. So here's heavensabove.com, and you can go in here and put in your location. So we just search for Vestal. There we are. We say update. And now we can go look at a whole batch of satellites, but we're going to click on ISS. And it gives you a data table with all of the upcoming flyovers. So we're actually in a pretty nice window right now, where in the early evening hours we can see the space station. Now, another critical point with satellites like the ISS, they will not have any blinking lights on them. It'll just be a steady point of light through the sky. That's why I kind of compared it to a planet or a star moving through the star field. Anything with blinking lights will be an aircraft of some kind. Okay. So whenever we talk about ISS2, I like to emphasize who's there. This changes every time we give a skies program because usually the expeditions change over the course of 6 months. So these are our astronauts that are on board the space station right now. This isn't the whole story either, I'll show you that in a minute, but there are 3 Roscosmos astronauts, these 3 here. There is 1 European Space Agency astronaut, and 2 NASA astronauts here and here, and 1 JAXA astronaut. JAXA is the Japanese Space Agency, ESA is the European Space Agency, and Roscosmos is the Russian Space Agency. So it is truly an international effort. And so that makes for your 7 astronauts that are part of Expedition 70. But kind of cool right now is that another mission launched the ISS on January 18th, and that is the Axiom Mission 3. And this is made up of, I think, entirely ESA astronauts. And the difference between your expeditions, like Expedition 70, is those are NASA and, well, I shouldn't say just strictly NASA. They're NASA, ESA, your government agencies operating those missions. But the Axiom mission is commercial. It's flown through a private company. So it's this collaboration between commercial space travel and space agencies from various countries. So in total, that means there's 11 people on the ISS. A little bit crowded. That's that's why they don't stay there for too long. I think they're scheduled to come back in early February. So they won't be there for too long with these Axiom missions. I think the Chinese space station has 3 astronauts aboard, and that makes for 14 people in space right now. So we always say when the ISS flies overhead, wave to the astronauts on board, and just in spirit. It's fun to know who's up there. And also kind of exciting is with Expedition 71 and the Crew Dragon 8 mission to the ISS, Jeanette Epps, who grew up in Syracuse, will be launching to the ISS for her very first flight into space. So that is very exciting. A semi-local astronaut will be heading up there. Okay, so there's the ISS. Like I said, you'll find other satellites up there too, but ISS, Starlink, the Chinese space station, those are all, the space stations in particular are going to be very bright, so those 2 will be really noticeable in the sky. Starlink can be very dramatic because they're visible to the eye, but early launch, like when a Starlink system has just launched, you'll see them as a train in the sky, which can be kind of novel until you realize that there's going to be a ton of those objects up there, and then you kind of get tired of seeing them. All right, but now we can get into the solar system, what's out there to observe. And one of the things that you can observe throughout the entire year, no seasonality to this, which is good. Well, I shouldn't strictly say that. There is, of course, during the winter here, we do have shorter days. So there is seasonality in that sense, but we will always see the sun where we are. We're not at the North Pole or South Pole where they do have periods where they won't see the sun at all. So we can always observe the sun as long as you have the right equipment, which is why I have that note of caution there. And I really bring this up because there is going to be a lot of excitement, not as we head towards spring, with this total solar eclipse on April 8th. And one of the big topics that Kopernik will be emphasizing is safe eclipse viewing and safe solar viewing. So if you don't think you have equipment to observe the sun, then you shouldn't be looking at this object. Like if you're unsure in any way, not a good object to look at. But that's our job at Kopernik, is to give you the tools to either figure out how to observe the eclipse at home or observe it at places like Kopernik. So that's why I really emphasize this point. Also, the sun is really interesting to observe with the right tools at this moment in its cycle, because we are in solar maximum, which is, they won't know for sure until they really capture all the data, but the estimate is this year into next year for solar maximum, and this is a period where the sun is really active. Its surface is active because you see all these sunspots. And these map out disturbances in the sun's magnetic field. So the sun goes through this solar cycle every 11 years, where it has a period of stability in its magnetic field, and then that magnetic field gets perturbed, and sunspots are a sign of that happening, and eventually that magnetic field will flip and rearrange back into a semi-state of stability. So we're seeing more and more sunspots. We're heading into this stage where the sun's putting off a lot of solar storms. We see a lot of spots, and it ends up being very interesting to look at. The other opportunity that this allows for are northern lights. There is a chance, I'm sure you've seen it pop up in the news over the course of the last year even, that, ooh, the northern lights might be visible here. And so far, there's just been a couple sightings here and there in ideal conditions. We haven't spotted them here at Kopernik because our northern sky does have a bit of a tree line there. So it is to see those northern lights, we would really need to have a powerful storm that can get above those trees a little bit. But if you go into the computer lab, there is an image of the northern lights from 2003 at Kopernik during that era's solar maximum. So you could go in that room and check that out at the end of the program. But it goes to show that it can happen, and they're monitoring it, and it's worth looking out for. If you ever see a chance of it and you see there's clear skies aligned with a prediction for northern lights, it's worth checking out, because this is the time of the solar cycle to do it. And then, yeah, just emphasize one more time, make sure you mark your calendars for April 8th with the total solar eclipse. And Kopernik will be talking much more about that event in the months ahead. Okay, we also have the moon visible throughout the year. One lunar cycle, meaning one going through all the phases, right? From new moon to first quarter moon, full moon, third quarter moon, back to new moon. That cycle plays out over the course of 29 and a half days. And that means just about every month you can go through a full lunar cycle and see all of its phases. Now, the one phase where you can't really see it, or even the crescents on either side of it, is new moon, because that's when we're looking at the moon in shadow. So not much to see there except for during a total solar eclipse, or even just partial eclipse. But this is a totally safe object. The moon can be bright, but you can look at it with the unaided eye, binoculars, telescopes, cameras. Even though it's a bright object, it's safe to observe no matter what. And it's a phenomenal object if you're a first-time telescope user. The moon is perfect for trying to learn how to use your scope and also appreciating the rich detail that comes along with our nearest celestial neighbor. Okay, so the moon's another one. Now we move on to planets, or maybe I should say planet, because there's only one, unfortunately, and that's Jupiter. Now it's a good one. And this was an image we took here at Kopernik during one of our live streams of Jupiter. And you can see some of its major features, like the equatorial bands that stretch across the disk of the planet here. And you also see this great red spot. That great red spot is larger than Earth, and it's one of the longest running storms in the solar system, running for as long as we've been able to observe it, which was back in the era of Galileo Galilei, who saw it in his telescope. And on top of that, you also have these features here, this dark spot, and can you kind of see that there's a little bit of a circular shape there as well? So this dark spot is a shadow. It's not a true surface feature of Jupiter itself, but a shadow. And then over here we have the source of that shadow, which is one of Jupiter's moons. I believe it's Io, if I recall correctly. Jupiter has four bright moons, 4 large moons: Io, Ganymede, Europa, and Callisto. Io is one of the smaller ones of that batch, but all of them can do this kind of projection across the surface of Jupiter itself. So this is an eclipse on Jupiter. If you were in that shadow there, you would, Io here would be blocking out the sun. So that's exactly what will happen on April 8th for us. So there's an eclipse into action on another planet. Now, if we go into Stellarium, I can show you where Jupiter is. The great thing about this star map here too is that because the website you can get these from is called skymaps.com, and they release one of these every month so that you can see exactly what's out in the sky during that period. And that means planets will show up there. Whereas if you have a sky wheel, which would be your star field mapped out across the entire year, and we make these during our classes here at Kopernik, those won't show planets because the planets will change their position through the months. So this is a great tool for finding planets as well. And if we go into Stellarium, we're going to go back to current time, and we're going to remove the grid just to clean things up a little bit. We'll keep the constellations on there because they can guide us as to where we'll find.
Is that picture of Jupiter you had up there the one Jenny took?
Yes, that's the one I took during one of our live streams.
Oh, it was during the live stream?
Mm-hmm.
Oh, okay.
That was, I believe, through our 6-inch refractor telescope.
It's a nice picture.
Mm-hmm. So this here, Jupiter, one thing that you could just track all of its data here, so you can see its magnitude is around -2. And I don't expect you necessarily be able to read that, especially those in the back of the room, but when you're using this at home, it gives you a whole host of data. And if you ever want to calm that data set down a little bit, you can go into information and just shorten it, which is a lot cleaner if you're not looking for every single little detail about this object. So, and it gives you your right ascension and declination there too. And it shows you its position relative to the constellations here. So you're looking around Taurus, the Bull, and Cetus, and Pisces, Aries, and Triangulum. So amongst those constellations there, closest to Cetus. And if we zoom in, we can take a telescopic look at this object to see its moons. It'll show you the 4 moons I mentioned, plus some of the smaller moons too, like Alpha. So Ganymede, Europa, Io, and Callisto. Zooming in more, we can see the surface details on the planet. So tonight, it does a decent job of predicting its surface features, and it does not look like we'd be able to see the great red spot. But if you, let's see if it pops out at all if we travel through time here. It might set before showing up.
That shows the angle of the planet?
Yes.
From our point of view at live?
Correct, yep.
Neat.
And you can see it's set there, so we can't see it anymore. But if we zoom out, it'll pop back up if we return to current time. So tonight you wouldn't be able to see the great red spot. It's on the other side of the planet. but if you scan through over the course of a month, you should be able to find periods where the spot would show up. You can also do the same thing with those transit events and eclipse events with the moons, and when you could spot those shadows. The images we take through our telescopes, like this one here, they are often a bit better than what the human eye would see, because you take a whole bunch of images and then stack them, so you can get a lot of detail out of it. But you would still be able to notice features like the spot here, like the shadow of the moon. Those still would be distinguishable to your eye, and the gas bands as well across the surface. Okay, so there's our planet for this time of year. Venus, you might be able to just catch in the early morning hours, but it's still pretty close to the sun at the moment, meaning there isn't a huge window where you can spot Venus just before sunrise. So Venus is out there too. And when we talk about planets during our skies programs, we're really talking about the conspicuous ones that you can spot in the sky with your eye. Uranus is out as well. I can show you that in Stellarium. But it's not one you see with your eye, along with Neptune. You can't see Neptune either. But in Stellarium, you can go travel to it. And a ground-based telescope like we have at Kopernik, you can see that when you look at it through the scope that there's something to it more than it just being a point of light. There might be a little bit of color that you're getting from it, because both of these outer gas giants have a bluish tint due to the methane in their atmosphere. But beyond that, beyond knowing it's not a star for sure, you're not really going to pick up too much else in a ground-based telescope like Kopernik. If you want an example of what the space telescopes are doing when it comes to planetary imaging, you can actually go see what Hubble has done with these objects and James Webb Space Telescope. And even then, they struggle to capture some crisp detail like you would see flying by these objects. Okay, so there's another planet out there, but not one that you'll see with your eye, and can be a little bit tricky to find through a telescope. Okay, bouncing back here. So we did this. Now we're going to get into our deep sky objects, and I'll show you the images first, and then we'll go hunt some of them down in Stellarium. So deep sky objects are they're going to be galaxies, nebulae, star clusters, these objects beyond our solar system, and maybe even beyond our galaxy, like another galaxy. And they're going to be more than stars, sometimes just a bunch of stars. So the Orion Nebula is an example of a deep sky object that we can see. You can actually see some of it with your eye this time of year too, or actually whenever it's out and you have dark skies. It's cataloged as M42. You'll see a lot of deep sky objects have a catalog number, M42, and the M in M42 stands for Messier, which is Charles Messier, who was a comet hunter. And this catalog were his not comets. Didn't know what they were exactly, but they weren't comets. He knew that. Because they moved with the star field. Comets don't. Comets you can actually see them move through the stars rather than moving with the stars like deep sky objects. So the Orion Nebula is a stellar factory. This is where stars are born, and one location in space. And this particular region of the Orion Nebula is called a trapezium. It's overexposed in this image, but it actually has a set of stars that take on a triangular shape. And that's the most active area of the nebula. You can see it's almost shaped like a funnel. Instead of stars falling into it, over time stars are funneling out of it. And the pinker areas of the Orion Nebula are actually emissive zones, so that's where light is being emitted out of these gas clouds. The bluer areas are just reflectance of stars. A lot of these stars are burning blue, and that's why you kind of get this bluish shade here. So that's the Orion Nebula. Then we have the Pleiades, or the Seven Sisters. This is, my guess is if you've looked up at the sky in the wintertime, you've undoubtedly seen this. Even if you didn't know what it was, if you've seen a cluster, like a very small cluster of stars with your eye in the sky in the wintertime, that's Pleiades. You're not going to see any of this nebulosity, this kind of glowing cloud around it. But what's neat about the Pleiades is if you start with, let me go back to the Orion Nebula. You start with this, a stellar factory. Stars are being born here. Over time, you run out of fuel, and you end up with something like the Pleiades, an open star cluster, where young stars are starting to spread out into space to form their own solar systems. And so they're still kind of clustered together, but over time they will continue to spread. And this also has another name. It is called, in Japan it's known as Subaru. Anyone drive a Subaru? Your logo on the car there is a grouping of stars, and that is what makes a Subaru Subaru. So, here's my joke for today. So, next up we have M35, an open star cluster as well. So this one is made up of more stars within it, but these are still young stars. This is as opposed, I don't think I have one in this show, but there is globular star clusters as well, and those are made up of old stars, some of the earliest stars in the universe that globbed together. So you're talking like red dwarfs and white dwarfs all stuck together in one clump in space. I shouldn't say stuck together, but they look like they are. They can be made up of like up to 500,000 stars, whereas open star clusters are fewer. You know, this one has quite a few in it, so maybe around 100 stars in here in this zone, but much fewer stars, and they are spreading out, not grouping together. Okay, so that's M35. Then there's this other set of open star clusters just below the constellation Cassiopeia in the constellation Perseus. A double cluster, so two open star clusters. And this is a great binocular object to observe. So some of these are so big in the sky that binoculars are preferred, because if you use a telescope, you're going to be zooming in on too much of the object. And with this one, because they're so spread out from each other, you can, with a scope, you'll really only be looking at one or the other. The binoculars are a better choice for this one. This is another object that's also really good through binoculars, and that's the Andromeda Galaxy, M31. It is our neighbor galaxy, and over time it's getting closer and closer to the Milky Way. It's also a spiral galaxy like the Milky Way. You can see its spiral arms here. If you've seen a desktop background that's made up of a galaxy, more often than not it's based on Andromeda, because you can get such crisp detail out of this object that's much nearer than the other galaxies out there in the universe. So you can see it also has a bright core making up the center of the galaxy. And in the sky, you can actually spot it with your eye at places like Kopernik where we get dark skies. And this is what it looks like, what it can look like at Kopernik. This, I think, was probably closer to fall when we took this image as it was rising up in the sky. Now it's more overhead as the evening begins. But this is our main building here, and you can see Andromeda right next to the radio tower there. The core is what shows up nice and bright, and then you have this diffuse cloud around it making up the star clouds and the spiral arms. So really impressive that you can spot it with your eye, but of course binoculars are going to make it stand out even better. So really quick, just jumping back into Stellarium, we'll take a look at a couple of these. starting since Orion is right there for us, we'll zoom in on Orion. I'm just gonna do this freehand, I guess, but there is a search function as well that you can use. So the Orion Nebula, as we start to zoom in on the constellation, I can bring up the artwork temporarily too to show you kind of the mythology of Orion the Hunter. But as we start to zoom in, you see this region has a star cloud in it. We continue to zoom. You can see just how big the Orion Nebula is relative to the stars here in the constellation itself. And like I said, you can spot some of it, the brightest parts of it, with your eye. And you can see that trapezium I was mentioning before here at the core that was overexposed before. That kind of funnel shape. So that is within the constellation Orion, below Orion's belt there. Great object too.
Not trying to stop you, but you know what the distance is?
That might.
Flare, give you that?
Yes, actually, that's a good point to bring up. I don't know it offhand, but if you go back
That's
to.
right, I wasn't trying to stump you.
If you go back to it doesn't show it in the data set I have now,
Right.
but if I can do all available, and it should give us a distance measurement.
The number I'm looking for, that's what I wondered.
Yeah, it says 884 light years. Okay, so that is Orion Nebula. Then we can go to Pleiades, which is of Taurus. Zoom in here. Oh, here. So Pleiades is part of Taurus the bull, kind of part of the body of the bull. And as we zoom in, you get that clustering of stars, and that nebulosity only shows up in cameras. It won't show up in a telescope, binoculars, or to your eye. So don't expect to see clouds around these stars. You'll just be seeing points of light with your eyes. Okay, and then we have, let's search for our M35. That's the one I can't remember quite. There we go. So here's that open star cluster we talked about before. Oh, there's another one nearby too. Both of these are open star clusters as well. And then we have that double cluster below Cassiopeia, which is up here. When you get to the zenith in Stellarium, it gets a little bit tricky to navigate. It doesn't really want you to go in the direction you want, but there we go. I think we lined it up right. And this is that double open star cluster we saw before. So those are all there, and you could just bounce around and search. If you wanted to go through the whole Messier catalog, you could do that. Some of them won't show up, but you just type in, I can't remember where it ends exactly, but you could type in M1, and it'll show you it's an object below the horizon, but you could go through the entire catalog that way. Okay, let's jump back here. So those were our deep sky objects. And to wrap up the show, because we have gone a little over time now, some tools that you can use at home even. First is Stellarium, which we've talked a lot about that, and I'm happy to answer any questions about Stellarium, either after the show or during our Q&A. But there's also other stargazing apps like Starwalk, Sky Guide, and Sky Safari. And I have those loaded up here too. I'll just briefly show you them. Here's Starwalk. These are all applications you can download on your smartphone. I just have them running on my computer here. And it's the same idea as Stellarium. This one I think froze up on me, but it's the same. All of these are the same idea as Stellarium. They just have different ways of representing the information. So here's Sky Guide. See if this one still works. Yep, that one's working. So you can kind of see how it traces out these objects as you look around. And on your smartphone, it will actually use the built-in compass. And when you hold up your sky map above your head, it will actually map out onto the sky based on that compass data, and it will approximate roughly where these objects are. And same thing, you have things like the Orion Nebula that will pop up in the field of view, zooming in and everything like that. And then if you want something really advanced, I wouldn't say it's worth necessarily like paying the money for if you're just starting out, but if you start to get your own telescope and maybe you're starting to image, that's where you jump to something like Sky Safari Pro. And this one you can actually even operate your telescope from. So like you could take your, you could link up your telescope to this application if it's a go-to mount, and then the telescope, you just click where you want to go, say go to, and the telescope goes and finds it for you. So this one's really powerful and does a lot for you, but again, if you're just starting out, one of the other ones will do just fine. In there, I think they all have free versions too, which helps. This one is.
Familiar with that one?
Yeah, this is the one I use a lot for my observing sessions.
I'm starting to use it, I'm beginning with it, and they offered Apollo missions, that they would, on that display, track the Apollo missions, and I'm interested in finding the reflector that they left on Apollo 11.
Oh, okay, yeah.
And its exact location.
Oh, I see, yeah.
And they said like $1.99 you can buy that package. Have you ever bought those little packages from these guys?
I haven't, I just bought the base application. I haven't branched out into the other, maybe add-ons it has. That sounds neat though. I'll have to check it out and see what that entails.
Yeah,
Yeah.
thank you.
Thank you. So yeah, they all work in the same principle. They're just modeling the sky. You can travel through time, map out objects. The feature sets are just a little bit different from place to place. And Stellarium has a mobile application as well, like I mentioned earlier. Okay, and then the last tool I recommend, went through these, is your smartphone camera specifically, which I would not have said this like 10 years ago. Except for maybe brighter objects like the moon. That back then it worked pretty well, but nowadays you can do things like this. And the best part about these images is, one, they were taken handheld. They were night mode exposures of about, I think, 10 seconds. So you just try and hold your hand as steady as you can over those 10 seconds so that you can capture enough light to put this star data together. And the phone's doing all of this. You're not doing any extra processing. I did not do any processing on these images. In fact, when I took these, it was as a demonstration for on one of my star tours outside. I just wanted to show them a little bit more detail than what their eyes could see. So I just took a quick 10-second shot, not necessarily ideal conditions, and this is what you get out of just kind of haphazardly pointing your phone up at the sky and using night mode. So in this image you have the Andromeda Galaxy, and you see the star field around it. You definitely see some artifacts from the processing that the phone does. There may be a couple of extra stars in this image. You see some weird clouding in the image too down here. So there are some artifacts that come along with just kind of pointing your camera up and taking a picture. But it is capturing a pretty accurate view of the Andromeda Galaxy. And then over here, we have Orion. So here are the shoulders of Orion. Betelgeuse, you see that reddish color that star is known for. Orion's belt. And right there is the Orion Nebula that the camera picked up. So your phone can do this, I bet. If you got your phone in the last 2 or 3 years, it most likely has a night mode, and you can take long exposures like this in the default camera app. So I strongly recommend trying that out sometime. It's not something you want to use on bright objects like the moon, but for stars, it works really well. And if you have a tripod, it will work even better, that you can put your phone on. So really powerful tool that you have on you at all times.
In clear skies.
And clear skies, yes, we definitely, if only. And speaking of,
Okay. Wow. You didn't pay me for that.
But maybe at Winter Star Party, we'll have those. Winter Star Party, as I mentioned, is coming up. Bring up the webpage here. We try to align it as closely to Kopernik's birthday as we can. Sometimes it falls perfectly on it. In this case, it's a day, I think February 19th is the official day Kopernik was born. But we're February 17th. This is a Saturday program. This is a little bit longer. There are different segments to it. Lots of announcements during Winter Star Party. Usually we have raffles during Winter Star Party. We do celebrate with cake because it is celebrating Kopernik's birthday. So, and that all starts at 6 p.m. Oh, and we'll have family activities too for that event. But yeah, with that does wrap up the Winter Skies program. I will take any questions you have. Also, don't forget that we have the sky maps up here too that you can take home with you for the January sky. Oh. Oh, and one last thing too for those that are in attendance here, because it's cloudy out, if you paid for admission, then you get a complimentary pass to come up again during clear skies, because kind of our rule at Kopernik is to be able to look through a telescope. If you're here, we couldn't fulfill that promise today. So you get a complimentary pass to come back the next time we hopefully have clear skies.
Did you show the clear skies on your website?
Oh, the chart? No, I didn't actually. That's thank you for the reminder there, because at the bottom of the web page, there's a clear sky chart that will tell you whether or not we are expecting clear or partly cloudy skies. What you really want to see on this is blue, and we're really not getting that. So just that white color you're seeing there is basically telling us it's overcast. So keep on the lookout for that in the future. It looks like over the next couple of days there's like not much of anything going on. Maybe heading into Tuesday there we'll see some clear skies start to show up. But that's a great tool for you to use, and it is specific to astronomical viewing, so it's handy to look that up.
So do we get an actual physical pass or just come in and tell?
Yes, you will get a pass if you go to the store on your way out tonight. That you get a card for winter pass.
Okay.
Don't forget to pass out the maps.
Yes, yeah. If you want, before you leave, you can come up and grab one, and then the passes will be available at the store. Yes.
Will the camera, the telescope and system be set up for the sun camera, and the telescope and that be set up for the eclipse?
Yeah, we'll definitely start rolling out some of those announcements and how we'll be both what we'll be doing here on site and also beyond Kopernik, how we're going to access totality. Some of those announcements will make it Winter Star Party, and then you'll see more information roll out over March. Any questions? Oh, yeah, is there any on the chat?
We do have one question regarding your Jupiter image.
Oh, yeah.
Mary asks, so if we were standing on Jupiter, not that one could, and see through all the cloud cover, is Io the right size to completely cover the sun from that point of view? And they ask because they read that someday in the distant future, our moon will be too far away from Earth to cover it completely during an eclipse.
Yeah, that's a great question. And yeah, if we assume that's Io, which is one of the smaller moons of Jupiter, smaller of the Galilean moons, it is close enough to Jupiter itself, and the sun is also much further away than here on Earth, so it's going to be even smaller in the sky. I believe Io will fully cover the view of the sun during those eclipse events. So it's just in that localized location, just like we see on Earth during a total eclipse. But I believe it does fully cover, so you go fully in shadow on that region on Jupiter. And then the other segment, what was the other part of that question?
Well, they mentioned that they read that in the distant future, our moon will be too far away from Earth to completely cover the sun during an eclipse.
Oh, that's right. Okay, so yeah, that's the other segment to it is that I think it's something like millions of years from now that our moon will be have drifted far enough away that we won't get total eclipses on Earth anymore. But for as far as our lifetime is concerned, we'll always have total eclipses on Earth. Any other questions? Okay. All right. There's one right here. Yes.
Do you know why cameras can pick up nebulas more than like a telescope could?
So it's based on like how you set up the settings on your camera. So even smartphones nowadays, like I mentioned earlier, they can do longer exposures, and that's something both I think on the Android side and iOS side, they've coined this night mode, and that allows the camera to capture more light over the course of a period of time. So you're in the traditional film days, you'd be leaving your film exposed over 10, 20, 30 seconds to capture all of that light from these darker objects. But now we're leaving the sensor open on the camera and letting that light hit to produce one image out of it. With a more traditional like mirrorless camera or DSLR, like bigger cameras, that's exactly what's playing out there. Is it's collecting all of that light over a longer period of time. Whereas if you just did a really quick snapshot, which is great for like things in motion, like if you're taking a picture of someone playing sports, they're moving really fast. That's where you just want a quick instant shutter, so it can capture that motion with no blur. But with these dim objects in the sky, you need to keep that sensor open and collect all of that light coming down from it, and that's how you start pulling that detail. Our eyes did not evolve to capture that kind of information. We can do a decent job just looking up in the sky and spotting stars in dark sky areas, but there just wasn't a lot of evolutionary benefit, I guess, to being able to see nebulae. So I guess that's the main difference, if that helps answer that question. Any others? Okay. All right, well, thank you so much for coming to Kopernik, everyone. So happy to have you. We'll see you maybe at Winter Star Party or on another clear sky.